Hey class, it's Bob Greavy here. I'm going to record a simple graphical linear programming problem solution from your textbook. So you're going to be able to watch as I graphically solve the problem in Chapter 2. I'm going to go ahead and write the problem on the board here. This is a maximization problem. The problem is to maximize, let's see, 5x1 plus 7x2. So this 5x1 plus 7x2, that is our objective function. x1 and x2 are our decision variables or controllable variables, and 5 and 7, those coefficients are some of the parameters of our model. Let me next list the constraints. We say we want to maximize 5x1 plus 7x2, subject to a couple of constraints here. The first one is x1 must be less than or equal to, that's supposed to be x1. Kind of difficult to draw using this smartboard. Let me erase that. Subject to x1 must be less than or equal to 6. The second constraint in your problem here is 2x1 plus 3x2 must be less than or equal to 19. Okay? The last constraint says that x1 plus x2 must be less than or equal to 8. Okay, so here's your complete problem. As sloppy as that looks on the board, it's difficult to write with this smartboard, but I think you can read it. So we have an objective function that says maximize 5x1 plus 7x2, and then we have three constraints. The first one is x1 must be less than or equal to 6. The second constraint, 2x1 plus 3x2 less than or equal to 19. The third one is x1 plus x2 less than or equal to 8. I'd encourage you to, and I should have said this at the beginning, to work through this with me. So you ought to be watching this video with a piece of paper and a pencil in front of you, and we can work through this together. Of course, hit the rewind button if you like. The first thing I'm going to do when I solve a linear programming problem graphically is I'm going to identify coordinates on the graph that correspond to the feasible solution space. In other words, that area on the graph within which feasible solutions exist. So let me make some sense out of that. What I'm going to do now is draw the axes of the graph. So this vertical axis, the vertical axis will be the x2 axis, and the horizontal axis will be the x1 axis. Now you could do it backwards. You could have x1 on the vertical and x2 on the horizontal. You'd still get to the same conclusion ultimately as long as you were consistent. But convention tells us that we put the first decision variable on the horizontal axis and the second on the vertical axis. So we've now defined an area that as I move up, x2 gets greater. And as I move down, x2 gets smaller. And as I move to the right, x1 gets greater. And as I move downward, x2 gets smaller. So any dot, here's the thing, any dot in this quadrant, in this upper right-hand quadrant of a graph represents a solution. So let me just put a dot out here. Here's a dot right here. So that dot would correspond to a solution. It would represent whatever x1 is right here. I don't know what it is. And whatever x2 is right here. So maybe these coordinates are where x2 equals 20 and x1 equals 12. Well, that dot represents a decision. Maybe x1 is the number of particular automobile to produce, and x2 is the number of mopeds to produce, as an off-the-wall example. Let me erase this and we'll go about solving this problem now. So let me reconnect the lines here. Now the first thing I have to do is I have to graph each of these constraints. Okay? So this first constraint, x1 is less than or equal to 6. That's going to be a vertical line, because what we're going to do is we're going to pick a spot in a minute where x1 equals 6, and we're going to draw a line on every dot on this graph where x1 equals 6. So that's going to be a vertical line that looks something like that, because every dot on that line, x1 equals 6. And then the constraint says it has to be less than or equal to 6. So this particular constraint is going to be talking about everything to the left of that line. Now, if we stopped with just the first constraint, my feasible solution space would be this area that I've shaded. Now, why did I stop at the vertical axis? Because we have these unwritten non-negativity constraints that say that, well, right here is 0, and our solution has to be greater than or equal to 0, so it's going to have to be to the right of that vertical axis. Similarly, there's a 0 here in the corner, and everything above the line, or everything below the line is off limits, because that would be a negative value for x2. I'm going to redraw these axes because they're a little bit sloppy at this point, and I want them a little bit neater as we wrap things up here. Okay. Okay, so let's draw another vertical axis, another horizontal axis. X1 will be the horizontal axis. X2 will be the vertical axis there. So now, you've seen how we graph x1 is less than or equal to 6. This next constraint, 2x1 plus 3x2 less than or equal to 19, that's a little bit more tricky, but not too bad. If you'll remember from your high school days, you probably graphed different lines that showed something like y equals mx plus b. You may remember that, where m is the slope, the rise over run, and b was the y-intercept. Well, in this situation, x1 is analogous to the x in that mx plus b, and x2 is analogous to the y in that equation. So what we have here in this 2x1 plus 3x2 less than or equal to 19 is we have a line we could graph. We have a relationship that's expressed mathematically between x1 and x2, and that relationship can be graphed as a line. If we forget this less than or equal to business and just treat it like equal to. So we're going to forget about the less than sign there, and we're just going to treat this as 2x1 plus 3x2 equals 19. Equals 19. And what I'm going to do there is I'm going to draw just a little t. Okay? And this is something I don't think you find in the book. This is just how I have always done it. And I'm going to draw x1, and I'm going to draw an x2. And I'm going to start by setting x1 equal to 0, and now I'm going to solve for x2. And in a minute, I'm going to set x2 equal to 0, and I'm going to solve for x1. And what that's going to do is it's going to give me two coordinates on this line that exists, on this line that is expressed by 2x1 plus 3x2 equals 19. So if you look at this equation and you say 2 times x1 plus 3 times x2 has to equal 19, and then you say, okay, we're gonna set x1 equal to 0. Well, that's anywhere on the x2 axis. So if x2 is, or rather, if x1 is 0, what does x2 have to equal? Well, I'm going to bore some of you. For some of you, you're thinking way back to high school. But what we're going to do is we're going to say 2 times 0 plus 3x2 equals 19. Well, of course, 2 times 0 is 0, so we're left with 3x2 equals 19. So if I have 3x2 equals 19, and I divide each side by 3, then I'm left with x2 equals 19 thirds, which is, of course, 6 and 1/3. Okay? 6 and a third there. So if x1 was equal to 0, that means that x2 is 6 and 1/3. And you could make sure you did that right. If x1 is 0, is x2 6 and a third? In other words, if we plug these numbers into this equation, will the equation be true? So is 2 times 0 plus 3 times 6 and a third equal to 19? And the answer is yes, it is. So we've done that correctly. Let me erase this right here. Now what we're going to do is kind of the opposite. We're going to set the x2 equal to 0 and solve for x1. So I'll go ahead and write it out. 2 times x1 plus 3 times, not x2, 0, because we're setting it equal to 0, has to equal 19. So that means 2x1 has to equal 19 because 3 times 0 is 0. We're going to divide each side by 2, and we have x1 equal to 19 halves, or 9 1/2. Okay, well, that's supposed to be a 2, not a 5. Let's see here. Let me fix that. Still getting the hang of this smartboard here. So x1 is going to equal 9 1/2. Okay, so let's come up here and put 9 1/2. And so what I've just done is I've identified two different coordinates, two different pairs of values that exist on this line called 2x1 plus 3x2 equals 19.